There's a lot of things that you said that are not updated anymore. So as for the CIREL, there are new directors now, so I'm not directors anymore. And for the there's other things going on. But anyways, let's go about the presentation of today. So how data can support optimization in public transport operation. So that's thank you for inviting me at such a CORS event because for at first I'm not really fully specialized in operations research, as you may know my research, but I collaborate a lot with colleagues who are experts in CIRET. And this is how, through the years, we've been, I would say, we gathered together the data part, which is more my specialty, and the OR part. And there's a lot now to be done because of the new advances, especially in artificial intelligence and how I will try to show you through some examples how data can help actually to build better optimization research model and we hope a better transportation systems. So, but short presentation, very simple for the short, I would say short plan. What kind of data we have in public transit, which is something that could be interesting for those who are may not may as I would say knowledgeable of all the data that is available. Some application examples, and the what's next is only to open the discussion about if you have any questions or any things you would might have to know about the presentation. So what kind of data we have in public transit? So I will focus on the data I've used over the year. Of course, there's many types of data set, but you will probably have heard about the first one. So first, I would like to stress what I call the object model, which was something, long ago published in my thesis. And the starting point of all my research is that we have to consider everything that's happening there, even though we don't have the data or even though it's not in a database form. So what you see here is what I call an object model. And in transportation, we have essentially four types of object. The first one is a static object, so something is just moving. In this case, the bus stop or the depot of if you look at the public transit authority, it's the garage or the stations or the bus stops. And the other types of object is what I call the kinetic object, which is something's moving. No, sorry, something's describing the movements. So, for example, a stop, a route stop, a trace, a route, so a transit line. So this is something that describes how the objects will move. And the dynamic objects are the moving objects. So essentially, in the case of transit, you have vehicles, you have users. So this is something you have to take into account. And the systems object are the objects regrouping other types like a network. In the case of the transit network, we have the train network, the subway network, and the surface network, which is the buses. So, and this helps to understand the relation. So I won't go into the details, but you have the relations between all of these objects. Some are encapsulated into others. Some are describing, some are collections of objects. And this helped to try to understand how the different objects evolves between them. And after that, we got to collect data about this. So the first obvious data set that you probably heard of is the General Transit Feed Specification, GTFS, which describes the planned service, the routes, the sequence of stops, the days of service, the geometry of the routes, the list of stops. So there's a lot of objects, a lot of tables in these cases, tables that will describe all the information needed. And this is planned months in advance. So for a service, you have to plan the schedules, you have to plan the routes, and it changes. It can change a lot. In the case of the STM in Montreal, it's about 4 or 5 times a year. They change the schedule and the geometry, but sometimes it's more the schedule than the geometry, but they can also implement new services. So this is in the GTFS, and this data source is mostly used in trip planners, Google Maps, Apple Plan, transit apps. So these apps will try to to propose itineraries or path. So they're using this type of data. So this is the first one we use. Uh, there's an extension to this is the GTFS real time. So in this case, it's the real time information. So it's a GTFS like we had before, like the one that was describing, but now it provides the updated GTFS. So corresponding to the real time, the real operation of the service. So the real times at each of the stops, if there was any detours, if some service was canceled, which happens a lot in large networks like in Montreal. So if there's a bus line that was not operated at this time of the day, so then we have this information. So this is more, but this is used also by apps like Transit and Google to provide real-time information. But actually, it's very, very interesting to have this data to know what happened there. So what was the operation? We also have other real-time information like AVL, automated vehicle location. So it provides the location of all vehicles at all time. In this case, it's mainly buses for sure, but there's some AVLs also for the train-operated systems. So, and we have for the location, it can be every point, every let's say 5 seconds, but usually it's more related to stops or events or a frequency that will depend on the type of system that's available, type of devices. And it's also used for real-time network management. So the operators use it to know where are the buses and how they can react if something's happening on the network. And it's also used by information apps, such as transit apps, can also use GTFS RT, but they can also use AVL. And GTFS RT is produced from the AVL data. Anyways, other things we have is automated passenger counting. So this is another information interesting. In many of the buses around the network, especially in Montreal, they have counting devices at doors. So they count the passenger in and out. Uh, uh, for sure, through the years, it's improved a lot. These counting devices were not very so reliable many years ago, but now it's more and more precise. So, and then this is interesting, but it's usually focused at stops. So this information when the doors open for sure, because passengers entering and exiting. It's not really real time. It depends of the system. It can be uploaded at the end of the day. In some cases, it's real time, but not as precise, only showing the load on board. So this is something used mainly for planning, for sure. They have to plan if there's the counting will show if the bus were empty or loaded, and it can be used also if it's available real time. Another thing that I've been working a lot with is automated fare collection systems. So smart cards, for example, or telephone payment or whatever. So it records every fare transaction, smart card, cash, tickets, and phones. In the case of Montreal, it also records the cash and tickets, which is very useful. In some places in the world, it only records smart cards, phone payments. So essentially, you have every transaction. So, and what is very important to understand is that this data is anonymized. So we don't have the real card number and we don't know anything about the users. And sometimes the card location has to be estimated because in the case of Montreal, the system does not record the location of the boarding, but through other means like the one we saw before, GTFS-RT or AVL, we can put a location on the tap-in transaction. If there's no tap out, because in most of the system through the world, you tap when you get into the system, but not when you get out, like in many places in North America, such as Montreal. So then we have to estimate the estimation. We have to estimate the destination of the transaction. So what we've done through the years, we're still working on this as today, is trying to propose algorithm or methods which are not really optimization, but it's more related to the sequence of the transaction. So we have somebody getting in a stop in the morning and then during the day they use another transaction. They do another transaction. So we say, okay, we try to derive the destination looking at the next transaction of the day. And we use the sequence of stop, we use the GTFS, and now we're using GTFS RT to do that. And it helps to estimate about 70% of the trips. But many users do not do more than one trip during the day, or they could do more than one trip, but use another modes beside. They could walk, they could take a big C. So now we have to refine this method. And what we do, we use the historical data. So for the user, we use the historical data of the card and see what are the habits of the user through a month, let's say. And then we can try to derive or estimate, okay, this user this morning was boarding at this stop. We don't know where the user was going, but we know that in the last month, we were able to estimate that the user got off at this station. So we propose that in this morning, they also got out at this station. So there's a kind of probabilistic event based on the density, a kernel density estimation. And now we are getting better and better in this type of algorithm. We're now working more on the missing data. So when there's missing data, and we try to complete every information we have in the data set. So our method is now used by IRTM and STM and other also operators that are they have to have this information, because when you have this, you have all the OD matrices for all the trips. So it's very interesting. And this is available weeks after transaction. So this is far to be real time, but this is valuable information for the transport planning and also the use in algorithms, like I will show in a few minutes. Other source of transit data, you have the surveys. For sure, we were working with that long ago, but we're still using them, the household surveys, onboard survey. They also have satisfaction survey, which is more related to the usage or the user of the system. We also have bus and assets maintenance. Sometimes, like the STM, they have a system, an advanced AVL data with many RT attributes for the real-time attributes for vehicle operations. So this is more, I would say, useful for maintenance and predictive maintenance management. So it's not my specialties, but I have colleagues who do that at Polytechnic. The crew scheduling and bus assignment. So there's a lot of work, especially in OR, about this topic. You probably know about JRO, the company from Montreal, and all my colleagues at Polytechnic and other university who worked a lot on the development of these algorithms, optimization. Social media data, we also work with this, tweets, reaction from passengers. We had some data from STM. We were able to estimate the impact of disruption. So using a little bit of AI and machine learning to analyze the tweets. And also public transit authority are still companies, so they have ERP data, so they have HR, finance, so there's all kind of data that could be related. And as I'm reading the slide, they have other data such as transit signal priority data. We also work with that in Montreal. So they can have a lot of data that is useful for the planners and especially for the operations research I would say algorithm development, which try to improve the systems, but to improve the system, you have to know what's in it. So this is something that we will discuss about. So some applications. The first one is one we've developed with I've developed with my colleague Catherine Morancy, and we're still working on this. It's the network design. So public transit network design is an old problem, very large combinatory problem, because there's lots at stake. What you try to optimize or to try to find the optimal transit network system. So in this case, what we do, we based it on the open source transition platform that we're also developing at Polytechnic. If you're interested, transition.city, which is a transition platform, is a platform that helps to plan and design a public transit system. So, but by hand, you do it with your knowledge. You can load GTFS files, you can export, you can organize your network. But what we said is, okay, let's try a genetic algorithm to use transition and to imagine or organize public transit systems. So have candidates network and try to find the best one. So this is what we did, a random generation of transit route from a set of predefined bus stops. So the bus stops are predefined, which is usually in cities something that is not out of the blue because they have usually already transit stops. And we can imagine that some major places or intersection in the city becomes candidates for stops. So we can put as many as we want, but they're fixed. And then we evaluate the scenarios using a transportation demand because it's not enough to have a public transit network. You have to put people in it and see, we evaluate which are the best in your when you evaluate and to be able to find a good one. And then what we found in this network, in this research, which is something that is over my I would say my talk today, is the importance to have precise data before having to optimize. So precise data on street network and a complete GTFS, especially the schedule-based GTFS. So I will show an example. The method is somewhat classical on an OR point of view. We have an objective function. We have to minimize the costs, which is composed of the cost of operating the transit system. So the number of vehicle hours that we need. And we have also to provide a cost for unsatisfied demand because if we just optimize the cost of the system, we will and we minimize it, there won't be anything running in the system. So we need to satisfy the demand and also have a cost for unsatisfied user or trips that cannot be satisfied. So this is something also we tested a lot of configuration. And then we have I would say, variables such as the demand, the cost of transit demand, travel distance, the fixed cost of unsatisfied demand, number of vehicles hour, everything. And we have an operating hourly cost, which is about $100 per hour in Quebec. But this is something you see here the variables, but you need to have the values. So the transition system provides for every network all the values that are needed to evaluate. And then this is an example of the interface of the system. So you have a transit route that is provided and with a sequence of stops. You see that some stops are not there because there are probably in other routes as well. And we start from a set of stop, we create routes, we evaluate, and we do genetic mutation, which as you expect in the case of genetic algorithm is to play with routes and set of routes and part of them and cut routes and just share between the different share segments between the different routes, keep the best networks and do it again. So this is what we did in this case. This is an example of the importance of using the proper tools and the proper data. What you see here is if you provide to Google Maps a sequence of stop, like the blue one, this is the route that Google Maps will provide you. So Google Maps doesn't have the intelligence to know that, okay, people can walk. So in this case, in red, you have the Google Map route. And in this case, in blue, it's our approach. So we have an approach that is using, yes, okay, the stops that are provided, but we don't usually follow the real, or we try to do what is logical for a bus to make. So this is very different. This seems very, you say, "Oh, okay, that's very simple," but this has an effect. Just in this case, if you use just as the crow flies, which is Euclidean distance, you see that here the percentage in the stops in the 10 minutes radius will be higher. This means that it people can access more easily public transit. But in reality, that's not the case. When you take into account everything of it, half of the people cannot access as easily at the public transit, which is more realistic in this case. So when we use the real data and all the support data, oops, sorry, we have a much better evaluation. So we use this method to Sherbrooke, Saguenay, and Trois-Rivières. We didn't use it for Montreal yet because it's very, very large, and then it's very computer intensive. A lot of it takes hours to calculate, but what we can do is to fix a part of the network, and then the algorithm will select for the rest. So this is something we are also experimenting. Uh, and the thing here that we showed is that there's an economy for larger network. This is obvious because if you have more buses, you can provide what was economy in case of the user per user. But there's also a kind of plateau or kind of stabilization of depending on the networks that we can provide because sometimes the geometry makes it impossible to provide more route or more to improve the system. So this is something also we tested in the case of this study. So this was the first one. The second one the we have is related to the operation of the network. So the last one was the network by itself, the design. Now we have buses on the network and we try to operate, and we also tackle what we could also say that it's a very old problem is the line transfer synchronization. So the goal here is to provide successful transfer opportunities to passengers. So when you are on a public transit, you want not to miss your transfer for sure. You want not to wait too long at the bus stops. So it is a very difficult task because it must consider the passenger demand. And there's a high stochasticity for sure because passenger demand can change from day to day. And there are a few options available to operators. They can hold a bus at the bus stops. So this could happen. They could speed up a little bit, especially in the suburbs network. Like we're working with Société Transport de Laval. So Laval is north of Montreal. And then they told us that yes, they can do some speed up in the case. They can improve speed, and they also can skip stops which are not very popular, but you can if in an ideal case you could also skip some stops because there are so many people on board that want to not miss a transfer, and maybe you will leave some one of the customer on the stops on the side. But this is not. They said okay, test it, but we won't probably implement this. But the two first strategies are something that is realistic in the case. So what we do, we have to take all flows into account. So this is an example here at the left. This is a space-time diagram, so time and space. Oops, sorry. And then you have an example here of a bus that comes, have two passengers on board, go to this, to here, and there's two passengers that are getting off of the bus. And then you continue here with, no, sorry, these are the two passengers are remaining. And you have two passengers arriving at the stop, then they have to take the next stop. And then they go into this bus to not the next stop, sorry, but the next bus. So this is the one bus. This is the next one. So they have to take the next bus. So they wait a couple of minutes. And then you have all the evolution here and also the information about the transfer on the network. So the passengers that are boarding off. And some passenger also have another transfer to make. Okay, here. So And without actions, this could happen. But when we take action on the buses, we can have the bus hold here, so we catch these passengers. We can also have action here, so catch the other passengers. So this is something that is can be done, and it will minimize actually the overall. So even though we make some passenger wait at the in the bus here, it can help because overall the overall amount of waiting time will decrease for all passengers. So this is the goal, the goal of the approach. And so what we do at the start of each iteration, we update the system with RT data. So RT data is actually what's happening before the bus stop. And then we also put we have to construct an optimization looking at all the potential demand for all the other trips following in a horizon, usually 5 to 10 or even to 15 stops, the next stops. So how this demand it is highly stochastic. So we use the historical data and we use also the real-time data when available, occupancy from APC, smart card data in the case of Laval, because we have to know who's transferring and where. So we use this data and we provide the most probable ways, most probable transfer for passenger. So this is all integrated in the online stochastic optimization algorithm. And then we evaluate scenarios, and then we update the system. We apply a tactic, we update the system, and then the next stop, we have to do it all over again. So each time there's a stop, the bus stops somewhere, we have to re-optimize to see what is the best tactic for the next. So when you look at online optimization methods, when you have these kind of methods, we generate scenarios. So then we use the consensus or the regret method. So consensus is try to generate multiple scenarios with tactics and choose one with the highest score. Regret, we use also a lot of scenarios, but we take the scenario with the smallest regret. So this means that we could have a scenario that is less, I would say, optimal in this case, but maybe because there are several of them. So it's a little bit like a neighborhood search. We try to degrade a little bit and see if we can make better in the next stop. And we also use the deterministic. So based on the mean historical values. So we don't provide scenario. We just look we don't do stochastic because in this case the scenarios are made with stochastic evaluation of the all the variables. So here we say, okay, there's two people in average that comes here at this bus every morning, but here we can do like go 1, 2, or 3. We have a little bit of stochasticity added. And then we also have the perfect information, which is the base scenario, the best one. But this is something that's just to make a baseline for evaluation. So the computational time relies on the combination of tactics. For sure, if you use the old tactic, we use old and skip stop, old and speed up. You have some, and when you use all of them, there's combinatory is very high, and sometimes it doesn't even, we cannot even have a good solution in a fixed time. So this is important because if it is a real-time system, we need a decision in the next 15 or 20 seconds because it's the time to go to the next bus stop. This is an example of results for Laval, line 42. So we compare, here you have, when you do no tactics, the individual passenger transit times of everybody. So, and when you use the consensus, the regret, the deterministic, etc. So what we found that is the consensus method is the best for this one. It provides, it helps to lower And the perfect information for sure is the best solution, but it is something that's not realistic. But it's usually better. It depends. It depends on the settling. But sometimes the deterministic is also good. Uh, but it depends also on the combination of tactics. So this is something we're looking forward to apply with STL, and they can apply some of the rules they have. Another third and last type of application we have is to try to optimize. This is a big word here. The bus travel time. The problem is that when you operate a transit system, you have to provide a travel time between stops because you have to provide a schedule to passengers. And then we have more and more real-time data now, but it's we have to determine how this travel time is organized. So usually when you have a bus from a stop to another, you have the inter-stop travel time. You have the dwell time, which is the time the door is open. And also, if it's an intersection, sometimes there's a red time. There's a traffic light signal. So this has to be taken into consideration. So with this student, what she's trying to do is to integrate many sources of data like GTFS RT, OpenStreetMap for the geometry of the streets, also AFC, which is a fair smart card to know and observational data to know who's in the bus because it's very important to have this related to the demand. And for each trip, she estimates the influence of the departure time, which is the time when you start the operation. So let's say it's the schedule of the first bus of the route, the speed you travel at, the travel light attributes, and the dwell time. So these four elements here are combined to create the travel time. And then she does an analysis on this case. And what she found for the case in Montreal is red light times is very an important time and an important part of travel time, especially in the central part. Even from some routes such as the PNF BRT, which is supposedly could be optimized also better for the travel time of buses. But even there, a large percentage, 20-30% of the travel time is related to waiting at traffic lights. So this is something that also is appealing to the planners. And then if you look here at this is an example for Route 27. This is the space-time diagram of the route, and all these red lines here are the traffic light, the signaling red, and then you see that you can plot the path of the bus. And what she found is depending of the first time of departure, you can have a lot of differences in the travel time. So this was surprising. So in many routes in the Montreal system, the starting time is very important to determine the travel time. So this is an example for Route 27. If you start, let's say here, you start at 6:39, the travel time is 1200 seconds. But if you start at 6:33, but also you have to understand that this depends on the number of people aboard. But even for very near here, let's say this situation here, we depart just 1 or 2 minutes before, and then we get almost 200 seconds less in the travel time. So you can have big difference, and you know that for public transit authority, time is money. And this is very, very interesting so now what she tries to do is to formalize a method that will be able to test scenarios for so it will be like an heuristic, but she's testing some scenarios on some routes and then try to provide the best strategies for these routes. So what's next in this case? What I've talked about is the usage of data, but also in a sense that we need in many optimization settings, we need good data. So it's okay to have a very developed OR method, but the problem is that sometimes it depends on the data you have to put in it. And this what I hope I tried to show a little bit, at least for public transit, that the data is essential. So yeah, we could continue to have, I would say, more theoretical models, but we need data. And the problem is that it's highly stochastic, especially in the case of people transportation, because people are not, people are very stochastic in the way they do their trips. Uh, and the other things we found is we have to include passengers into buses. So there's a lot about service optimization, especially in the literature, but you have to put people in the buses. Just showing an example, if you want to, like the work from my student Laura, if you want to optimize the system, there's maybe a way to consider more the buses that are with more people in it than the buses that are empty. So this is something also we're looking forward. And in this case, stochastic approaches are much needed to better consider the ground truth. But there's a lot of preparation of data and a lot of analysis of the data that is needed before you can go there. So this was it. So I suppose you have questions and comments about the presentation. I'll be happy to answer to your questions.
Thank you very much, Martin, for such a nice presentation and giving an overview of how the data is important for a public transit operations planning. So now the floor is open for questions. If you have any question, please ask. Prince has a question for the speaker.
Uh, okay. Good morning to everyone. And Professor, it's a very nice presentation, and it was really nice chronologically, and also I have much interest in your area as well. My first question is about the data,
Mhm.
because for me, for instance, I'm not having a car, so I use the Montreal STL. Uh, so you talk something about you saw about data, but one thing I did not hear about is data technologies like Kafka or Hadoop or those kind of big data analytics systems whereby I have inbuilt analytics. Because I also
Yeah.
heard about when you say that if you want to trace the route of maybe a passenger, because what I know is that when you are getting into the metro, we tap in. After we tap in, when we are moving
Yeah.
out, we don't tap out.
Mhm.
So how will you trace that? Maybe there's a problem. But at times, situation whereby there's a lot of, maybe if there's an incident, you see the police will be tracing the person from one metro to one metro. It's a big
Yeah.
problem. But if you have a tap out or something like that, it'll be easy for
Yeah.
them to, yeah, to get. And that's the first thing. That my first. And the next thing is about the payments. I heard
Yeah.
about the cars and other stuff. Where it takes a week for to get analysis of everything. So I was also suggesting if they can use blockchain when it comes to the payment of the uh, uh, transportations, like using Bitcoin or maybe other blockchain technologies, because
Mhm.
that will easily make us trace. Like within the week, you can get to know that this person bought this item from here. Because I know blockchain is another technology that is evolving now and changing a lot of stuff when
Yeah.
it comes to um, this. And also, I don't I've never heard anything about the security measures when it
Yeah.
comes to the system that you built, like your system that you have. So if there's anything, because since most people are also trying to find ways and means to use the transport system freely when it comes to other way around.
Yeah.
So that is the other thing. And my major thing, and it's also run through your representation, like optimization of this optimization. It's very nice because optimization is the best thing to know to reduce times and also make things efficiency. So I like your presentation and thanks very much for your insight given to us today. And I do really appreciate it. Thank you.
Okay. Yeah, there's a lot of things in your comments. I suppose you are in computer science because you have questions that are So the first one is about Hadoop and these database and these larger database system. In the case of the ST, but I work with STM and STL. It's not no, it's not billions and billions of. It's a couple of gigabytes per day, but it's usually stuck in traditional relation. I think relation models, database, relational database, but they're also used this kind of tools. I've worked with Exo, which has the snowflake, and they had because they had air data, which is data on traffic, and my students were working on that. But I'm not involved in these discussions. Sometimes they discuss with me, but it's not part of my research. But I know that in Laval they have a data lake, which is very, very complete. Laval has probably the best data system over the Quebec transit authorities, and I would say in North America, I'm sure if I say that they have the best system because they integrated all their data. So this is nice for the estimation of the tap out location. This is an issue we have since almost 51 year now, and we're working on this. So what we do is an estimation. So we're not sure about the actual destination, but we also use some tap in, tap out data that we had from an Australian partner because in Australia they have tap in, tap out. We applied our method and we found that the results are quite good actually. So people are yeah, they're a little bit stochastic, but they're very predictable. If you use the subway in the morning, but the subway you don't have too much place to get off. If you use then in the afternoon the another route and then the route is connected to the subway, we can suppose that in the morning you got off there, but we don't have any proof about that. So this is the thing. But on the overall situation, the estimation of the passenger kilometers, and we also look at the boarding data. So we're working now with a transit authority in France where we apply the destination algorithm, but we also use we also look the passenger counting on board the buses. So we're sure we adjust if the estimation to be sure that we get in touch, we are involved with the actual number of
Sure
passengers.
numbers. Okay.
Yeah. So this is another first thing. I will go through security. Also, this question has been the privacy. We for sure the data is completely anonymized. In the case of the Montreal system, it's an irreversible encryption of the card number. So we don't have any. We can't get any information about that. But there's still, yeah, it could be an issue. But like I say to everybody, it's is it worth two smart card transaction per day or your Google phones in your pocket and can follow everything you do? So I think it has to be related. But yes, they taking the measure very seriously. And for the fare evasion, this is something also that we analyze through the years because when you have smart card and you have passenger countings, you can actually estimate the fare evasion, so the fraud in this system. So this is something we did also with the STM in Montreal. And the last thing is about the payments. So blockchain and using blockchain is very sexy, but actually I don't think this would apply here because it's like $2 financial transactions. So it's something that can be tackled in regular payment system. They do it all over the place, all over the world. There's no problem about this. And when we usually the problem in Montreal is that they have to change equipment, but it is not rocket science. You can get anybody to pay with a phone or with any device, and this I think will improve. But the processing will be the same. If it's smart card, if it's phone, like in Laval, they have credit cards also, physical credit cards payment and also phone payment. So it's the same data that it's collected at the end. So this is something also. What is expected, though, is to be able to trace the card from a day to another. When it's a smart card, it's much easier. This is very nice for long-term transit planning, but sometimes in some system there's no way to retrieve the same user from a day to another. So that makes it much difficult, but there are also methods to cope with this situation. Thank you for your comments. I don't know if anybody else has
Okay.
question or.
So are there any other
There
questions
was
for the
one in the
speaker?
chat, I think.
Okay. Yeah, okay. Two people have messaged on chat. Let me have a look.
That is
So,
interesting. The first question is about the quality or the kind of people that is this is an interesting question actually. It is true that the transit authority do not already have the mankind or the manpower, the women power to, but it's changed. It's changed, especially in Quebec. Maybe it's because of us, because we we train students and now they're in the places. But yeah, it's true that this could be because it's not the first job of authorities is to drive buses and to carry people, and it's true. And but they have now better ways to collect data, but they don't always do much with the data. So that's a thing that we try in the through the years to, especially for the fare card data, the smart card data, nothing was done with that. It was only for accounting. But now we show them that something can be done. GTFS RT also is not really used. It's mostly used for, online viewing of data and user information. But now we're getting into it also. So yeah, the question is very relevant because we need I would say HQPs, especially master students and even PhDs. Laval has two PhDs in their planning team, so this helps a lot when you get to. That's why they are the most advanced also. So it pays to have highly qualified people to do this kind of job, but for sure it's also related to the resources that they have and the ability to hire people. Oops, sorry, Anjali, you're muted.
so thank you, Martha. Simon, is your question answered? Okay. So he writes, what is usually the main limiting factor that prevents companies to use these kind of technologies, access to data, having highly qualified employees?
Yeah, that's why I just answered. It is true in this case. It becomes mostly, but it's for many transportation companies. We need qualified people, especially to understand the data. The first thing is to understand how and understand also how it evolves. So we need the data analytics facilities, but usually they have the usual suspects, Microsoft BI or something like that. But it's not enough. You need to organize the data to be able to show the good indicators in these BI and table and whatever tools you are using. So
Sure. Thank you, Martin. I will ask maybe one question just for my own clarity.
yeah,
So in transportation problems, you talked about, the network design and
yeah,
synchronization and many more. So these are actually very complex problems. And when we are talking about addressing these challenging problems, there is issue of dimensionality. That means your network can be very
yeah.
big. And in addition to that, you have challenges to address, such as number of transfer stations and many more. So so is this part of your problem as well? Because a big number of buses and then all these
Yeah, it's a
associated
good
problems at
question.
one stop itself can be very complex, and we have
Yeah.
so many stops in picture. So are you also addressing these like dimensionality problems of the?
Yeah, this is a good question, Anjali, because in Laval, for the example I showed you, first the student work on only one route at a time, which
Mhm,
is simplifies a lot, but still there's thousands and thousands of. But now she's working on multi-routes, so on the network side. But
mhm.
what we found is that, and it's obvious, is that if we work with routes that are not really connected together, it's better. So we cannot optimize routes one by one, but then when we try to cross with several routes, this amplifies the problem. But she's working on this. But it's still Laval network is not a big one. It's maybe 50 or 60 routes with 1,000 stops, but we're not at the STM yet. It's very, very much complex. And the problem is that when you use just part of a network, you have to fix all the other things, and you need solid demand data, because the demand data is this is changing all the time. So, like for example, in my students in Laval, she used 30 days of data, but each day is different.
Mhm.
But so this is something that has to be taken into account.
Okay. And the second is more of an observation that, for example, here in STM, we have quite good access to, close stops, and we can get a bus when we need most of the
Mhm.
cases, but it may not be the same situation in many other cities. So
Yeah,
for public transit, maybe, the network coverage that the transportation system wants to provide and the minimization of cost, they are not, mutually aligned. So,
yeah.
is there something like the STM has more weightage on coverage over cost, or it's a best case study? What is your say on this? Like, because these two objectives are, coverage versus cost are
Yeah,
conflicting. So, what would you say, or what
yeah,
would
for
you
sure.
prefer over other?
Yeah, but STM is because of the density. That's why they have such a system. But when you go in the western part of the island or the eastern part, the service is not so good. And also in Laval, this is why we use this case study, because people can wait a lot.
Mhm.
Sometimes you have 30 minutes at ways, 20 minutes at ways. In Montreal, it's less the case in the central parts, so I would say it's less damaging to miss a transfer, but in Laval, so that's why they are very interested. But the other thing is that, yeah, public transit is not making money. So this is another thing. And we hear a lot about DRT, this demand responsive system. There's a lot of research about this. And the problem of DRT is that it costs a lot. And then we cannot have a bus or a car driving everybody in the morning. It's impossible. It's too costly. So that is why DRT is seen like, I would say, like a transition solution before having a real bus or train system. So this is something also that's not already clear in the literature, because people like to, it gives very complex routing algorithms, and that's nice for science. But
Mhm.
in reality, we don't want DRT, because DRT is costly. It's very much more costly per trip than a bus or a minibus.
Okay,
So
thank you very much,
thank you.
Martin,
Thank
for
you to
your
you.
great presentation and insights on the subject. I would let the audience know that Martin is a seasoned expert in the area, and we are so proud to have you with us today. Thank you so much, Martin, for your
Thank you
topic.
to you.
And now I will pass it on to the second speaker, Professor Gouging Zhang. Dr. Zhang, are you there?
Yes, I'm here.
So
Yeah,
So
thanks.
I will now pass. Thank you once again, Martin. And now is the time for our second speaker, Professor Gouging Zhang, who is also a very known expert and editor also in the area of supply chain management. I will present his brief bio, and then we'll pass it on to Professor Zhang for more details. First of all, I would like to say special thanks to him for accepting our invitation. It is our great honor that he is with us today for our course micro event. Professor Zhang is a professor in industrial engineering in the supply chain and logistics optimization research lab at the Department of Mechanical, Automotive and Materials Engineering at University of Windsor. His research interests include supply chain management and optimization, operations research, manufacturing modeling, e-commerce, warehouse management, data-driven optimization, machine learning, and intelligent decision support systems. He has published over 100 articles in these areas. Dr. Zhang's research is supported by NSERC, MITAX, and Canadian Foundation for Innovation. He has provided consulting services to several world-leading companies in the automotive, energy, airline, and food industries. In 2015, his team received the CORS Practice Prize. In addition, he has developed a solver for large-scale linear programming based on the interior point method. His talk is entitled Integrated Supply Network Optimization, Machine Learning Assisted Solutions. So I will pass it on to Dr. Zhang for his talk.
Okay, thank you. Thank you for your invitation. It's my great honor to give this presentation. Yeah. Also, thank the audience attend. So next, let me share my slides. Can you see the slides?
Yes, we can see
That's
that.
good. That's good. Okay, good morning, everyone. So I like to show a couple of works our research group have done, include ongoing project. So just as President introduced, the title is Integrated Supply Chain Optimization. We introduce a method about use of machine learning assisted approach. Today I like mainly present the two aspects. The work first is about smart supply chain management, and the second is for the specific location production routing problem. Because what we are doing, I like to say we can put those work under the smart supply chain umbrella. So not only this work and some other works. So I like to show what we did about in this area, review what we had. So this is about the smart supply chain management in Industry 4.0. We mainly focus on some research agenda and strategy in North America, but the paper is based on the literature. Yeah. So what do, this is joined work with my previous postdoc and research associate. So we use different resources for this review. For example, we use reviewed some national strategy in US and Canada, and we reviewed ongoing research project from the NSF and NSERC, and we also look at those papers. We mainly like to look at the Industry 4.0, those relate to the advanced manufacturing and the smart supply chain on the Industry 4.0, and also research trend and applications from those aspects. Yeah. So when we talk about the smart supply chain, there are different definitions. So here we mainly refer to the definition given by the Wu in 2016. We make a little bit change. So supply chain that integrate partners, self-organize, and automatically adapts to environmental changes, and make intelligent decisions that best achieve business goals. Yeah. I like to see this definition. I like to see the central is AI and the machine learning. Yeah. The characteristics include being the integrated, intelligent, adaptive, and self-organizing. Yeah. Of course, this smart supply chain has a different stage from the initial. Some part has a intelligent function and go into the whole supply chain. Yeah. When we talk smart supply chain, we always link with some those technology, especially information and communication technologies that link with the Industry 4.0. For example, cyber-physical system, Internet of Things, cloud computing, 3D printing, blockchain, big data, and AI, machine learning, digital twins. Even recently, I like to say the quantum computing. All those technologies are the basis for the smart supply chain. So here we see we have a digital supply chain, use those just mentioned technology, ICT. And then with the digital supply chain, we can have a lot of data and connect the different parts. Then we use those data for smarter supply chain decision. Yeah. So for example, right now we use a lot of RFID system. So the data is available for those logistic and the transportation. And also just like the Martin's presentation, a lot of the public data available. So based on those data, how can we make the smarter decision? So we proposed a smart supply chain framework. That is have different levels or different stages. For example, level 0, we see that is a base, like those kind of technology, ICT and AI machine learning. I take it out specially because this is a key basis for that. And the other advanced manufacturing robots and other development. Then we use those kind of technology. We can have a fourth level, that's called the level 1 smart supply chain. In this level, we mainly support, for example, just one flow, material flow or information or finance, or one driver, for example, pricing or inventory, or we can make the decision in the one level, like the operation level or tactical level or strategic level for that. For example, we have a lot of decision problems in supply chain. We can separate those levels. We see a lot of publication already focus on this area. The goal for this stage is mainly for the smart function and increase visibility and have real-time data and get optimized for the process. So we can see a lot of publication on this area. And the second level is we have a smart supply chain or network together. So for this level is not only just deal with one driver. For example, they can combine, for example, inventory and the transportation together, like the inventory routing problem, and this kind of integrate the problem and make the intelligent decision, and also in those area and range, we have a self-organizing the process. So this also, even in the level 2, we have a range from the in combine two partner, for example, two drivers, then go to the multi drivers even more for that. So in this stage, we mainly focus on the supply chain responsiveness, efficiency, and resilience, flexibility, and also the sustainability. This is a second level. And the third level is our supply chain will connect with the other system, not only just supply chain. For example, we link with the public transportation system or other systems, smart city, then have a integrated system. So we will not only consider just economic aspect, maximum profit or something, we also need to consider the society and environmental impacts. So that is a different stage of the smart supply chain. So I like to see most recent work mainly focus on the level 1 and level 2 for use those technology for the supply chain. So here is about some national strategy on advanced manufacturing and the supply chain in the North America. Yeah. So I like to see advanced manufacturing is a high related with our supply chain, because supply chain is an important part to support the manufacturing. Yeah. So I like to say in the States, almost every 4 years, they have a national strategy issued linked with the advanced manufacturing situation. Yeah. And here I just list some of them. And the different strategy, they will update the new technology linked with that, and also with a different supply chain focus for that one. Yeah. And also in Canada, we also have a similar strategy or policy. For example, Canada's Innovation in the Skills Plan in 2016, and in 2022, we have a Canadian National Supply Chain Task Force. Yeah. So this is a little bit late. For example, 2022, in the States, they have a 1-year national report, mainly focused on the American manufacturing and the security critical supply chain. They give a capstone report and list 6 key industrial sectors. Yeah. In 2023, they also announced the president announced the new actions to strengthen America's supply chain. Yeah. So here is about those 6 key industrial sectors, mainly energy, transportation, and agriculture and food, and the public health and the biologic, those aspects, and the information communication technology, and the last one is defense area. So those are the 6 key industrial sectors included in the report. I like to see this kind of national strategy on the supply chain, and some even in advanced manufacturing does affect the supply chain strategy decision. Yeah. So we can see this is a report about the supply chain resilience, deeply connect the macroeconomic activities. You can see the supply chain bottlenecks contribute or respond for the significant share of the inflation in states between 2021 to 2022. You can see the inflation, the increase now. So that's the research show the supply chain resilience is one of the main reasons for that. Yeah. So in the 2022 in states, they have a floor initiative. This is called the Freight Logistic Optimization Works. This is a kind of public-private partnership, and is a shared industrial platform. The purpose for this platform is to enhance supply chain data sharing and improve the efficiency of goods moving across United States. Yeah. Participants include the cargo owners, ocean carriers, ports, terminals, railways. Yeah, this is open, and they encourage more stakeholders to join. Yeah, this is running by the U.S. Department of Transportation. Yeah, so that's already 2 years. They recently issued a report. A lot of data available there. So when the company join, they can enjoy or take the advantage of the data and have a good forecasting about the logistic and the supply chain process. Yeah. In Canada, we also have a similar strategy. In 2022, Transport Canada also have a establish a national supply chain office. The goal is to examine domestic and international supply chain issues and encourage the data sharing and using digital tools, and also help the government and the industry make smarter policy and the investment and also other decisions. Also that you will develop and implement a national supply chain strategy and help the federal government respond to any supply chain disruption in the major area. Alex, I'm not sure if we already have the state floor, the platform, but I think probably we'll have that system soon. Yeah, so that is some international national strategy related to the supply chain. Next aspect is about research agenda on those new technology. I mainly reviewed those projects from NSF and NSERC. So with that search those database, I found those ongoing research projects sponsored by NSF and NSERC. But at that time, and when I do the search, the database is 2021. Recently, I tried to update to search from 2021 to 2023. I have a little bit data on that. But even in the that time, from 2015 to 2021, we can see what kind of research project were going on at that time. So you can see we look at the big data, Internet of Things, cyber-physical, and 3D printing, cloud computing, blockchain, AI, machine learning, Industry 4.0. We look at both NSF and the NSERC. So we looked at the project with that keyword in the both abstract and title in the first column. And the second column is only the title, including the keyword. And the third column is applied to supply chain related. The supply chain can be any supply chain aspect. Can be supply chain network, inventory, and all those different drivers. So you can see we have a lot of research projects ongoing on the different technologies. When we go into the title, only that is narrowed down because we see the project more focused on this technology. And we also look at the supply chain. So you can see those three numbers definitely increase from low 1 go to low 3. But you can see the number dropped dramatically. So you can see applied to supply chain, the project is very limited, very limited. Similar situation also in the NSERC. NSERC situation, we have the abstract and the title, those kind of projects, and the title only. And here, this number, two number, because that time we don't have 2021, we search other resources posted on the website from NSERC. And here is the number in Canada, NSERC here, we have a number applied for the supply chain aspect. Similar like the NSF, so the project is focus on the supply chain aspect is not so many. So here we can see based on those data, big data, AI, machine learning are the hot research areas that both NSF and NSERC have a highest active projects. But ongoing projects that focus on the impact of those technology on supply chain are relatively low, except the machine learning in NSERC, we have 22 at that time. usually just 5 to 12 projects for use those technology, each technology on the supply chain. Yeah. At that time, blockchain is relatively new, but they do have some projects already appeared. Only 6 and 2 applied the supply chain area in the NSF and the NSEC. Yeah. I looked at recent data from 2021 to 2023, 3 years. Yeah, 3 years projects, ongoing project. So we have 10 NSEC projects on the blockchain. 2 of them link with the supply chain. Yeah. Another technology is about digital twin here. We have 4 NSF and 9 NSEC at that time ongoing, but only 1 NSF project related to the supply chain. I also looked at the NSEC from 2021 to 2023, which is approved award. We found 172 NSEC projects work on the digital twins. That's a lot, but only 10 relate to the manufacturing, and 4 link with the social network. I like somehow link with the supply chain, but not many actually link use digital twin in the supply chain as a research the focus. But interesting thing, yes, we can found a lot of paper literature work on this area, apply digital twin in the supply chain. Yeah, but the research project is I don't know what's the reason. There are not many for that topic. So we can see, compare with the articles we can find the number and the scope of projects on the ICT in supply chain less than expected. Yeah, less than what I thought at the beginning when I work on that one. So how to facilitate research in this area and overcome the barrier is I like to say is a topic needed to start. Yeah. So why we don't have more project focus on those topics. But I like to see the machine learning and AI aspect. Recently, I believe a lot of project. I searched the machine learning, for example, in 3 years, we have 820 projects supported from 2021 to 2023. But I haven't got a chance identify how many projects link with the supply chain area. Yeah. So here is we also do the literature review part, but I'm not going to show those literature review, but I just summarize those different technology applied for the different stage of the supply chain. For example, our supply chain can look at the from the source, make, delivery, return, and enable. This is actually the APEC supply chain model. Yeah, they give this different stage, and we can see different technology used mainly focus on the different stage. For example, cloud computing mainly used for the manufacturing stage, deliver, and also enable. Enable mainly focus on the management aspect. Yeah. And here, 3D printing mainly used for the manufacturing, making process, production stage. And the Internet of Things is almost for every aspect except not much on the manufacturing. And big data also is mainly focused on the sourcing and the return. Actually, this can be applied to all aspects. Yeah, but this just highlight what is a main application in the literature. And the blockchain mainly used for the sourcing and the return aspect. Yeah. When we use for the source, we mainly increase transparency, security, and reduce cost. So last low is mainly is show the purpose for that. And in the manufacturing stage, mainly for the automatic and speed up and also flexibility for manufacturing. And here is in the deliver stage, mainly focus on the how to monitor the the process, logistical process, and also the efficiency, and also the automatic process. And for return, we mainly focus on the tracking, for the stage, sustainable and recyclable area. And the last one is mainly focused on data-driven, system-wise, the whole system range, and also for those different challenges. So those just show the different technology applied to the different stage of supply chain and the main function. With those review from the both literature and the projects, also in concern the national strategy, we proposed some research topics in the supply chain management in Industrial 4.0. I like to see we have a lot of new challenges recently. For example, we have many several years back, we see the globalization affect the supply chain. But recently, we have a lot of trends. See, from the globalization go to the localization. So how it affects the supply chain? Definitely, this is a important topic. And even recently, you can see the states and the new elected president claimed they will have the tariff on the different countries, including in Canada. Those kind of policy affect the supply chain a lot. So that is I also recently we see the different discussion on this aspect. But here we go back our research topic. I just see those kind of new situation will bring a lot of challenges to the supply chain. So here we see the research topics like the AI and the machine learning in the supply chains. This I like to see this is essential to the topic. Almost every aspect from forecasting to the delivery stage. And the second is about the smart supply chain with a new business model, with emerging those technology, such as on-demand platform, omni-channel or live stream business, or last mile delivery with Zhang, those kind of area. And another is about human-centered and ethical ICT in supply chain. For example, the worker-centered Internet of Things, how to manage internal aspect, and also the ethic aspect. Even we use those Internet of Things to have a lot of sensor linked with different equipment. Even sometimes we may be linked with workers for that. And the fourth one is about the blockchain technology. The last presentation also mentioned this application. This mainly used for the traceability, trust establish, and smart contract. And next one is distributed manufacturing supply chain with 3D printing. This is a topic later on I'm going to talk for our project. And another is about AI support modeling and algorithm. This basically is use machine learning to improve the algorithm optimization aspect. Also for the modeling, how to change the the model to adapt different situation with different environmental situation, I like to say. And another is about the smart supply chain engineering. This mainly focuses on the hardware part. For example, the auto warehousing. There are a lot of companies right now already use half or full automatic warehousing. And also about industrial Internet of Things based network and system. And another one is digital twins in supply chains. As I mentioned in the project right now is not many, but we have a lot of papers already. Last one is about the quantum computing to address supply chain optimization. Yeah. So all those I like to see have a lot of research problem or challenges. Yeah. Here, this slide, I like just narrow down to the new supply chain optimization problem. So when we look at those kind of new problem, what kind of challenges we're facing, and what kind of new problem we can work on, include the solution method. So here, for classical operations management and supply chain management, we have different decisions on the strategic, tactical, operational, different level. Yeah. And then we can combine with those 4 aspects. I like to say, for example, one is ICT. I just mentioned, like Internet of Things, cloud computing, AI, big data. And the second one is about a new business, like I just mentioned, the omni-channel supply chain. And another one is about the new situations. For example, COVID-19 situation at that time, and after COVID-19, and also right now, for example, I just mentioned from globalization, transport to the localization. Yeah. And another is about environmental and society aspect. So here, each of them combined with a classical problem, we will concern the demand, will form the new supply chain optimization problem, like different areas. For example, if we combine with the environmental aspect, we have a green reverse closed loop supply chain aspect, and also like the more high level different industrial sector, how to link them together, concern the environmental aspect. And if we consider the new business, for example, we have a dual channel, omni-channel, and also have a digital supply chain aspect. Yeah. If we consider the new situation, we consider how to build the international global supply chain, if we consider the globalization aspect. And ICT, of course, can lead to a lot of new problems, like I just mentioned, digital supply chain, also one of them. And last mile delivery with Zhang. Just name some of them, digital twins, a lot of opportunity I like there. Yeah. So with those kind of new area, combine those each or multi aspect or those 4 or 5 aspects, we were going to have a smart and a resilient supply chain. Then we will have a new supply chain optimization problem. For example, we will have an integrate optimization problem. As we say, the smart supply chain second stage, we link with different drivers, use ICT, and we'll deal with the uncertainty and the disruption aspect, and link with the supply chain risk. We have a new optimization problem at that one. And with the internet, we have a lot of data-oriented problem, use data-driven, and also the dynamic or real-time situation, how to quick response, how to adjust our plan and the scheduling, we then can form the new optimization problem for that. Then once we have a new optimization problem, usually they are large scale, difficult solving. So we need to develop a new optimization, even method or algorithm to solve those problems. For example, data-driven, or sometimes we use simulation-based, and we have a multi-period dynamic program, and also use a control serial dynamic modeling method, and of course the machine learning combined to solve the optimization problem is a very hot topic, and also the trend for that. Also recently we use quantum computing to solve the supply chain optimization problem. So we can see a lot of new supply chain optimization problem. We need to find the efficient solution method to address those kind of problem. So this gives us many research opportunities. Yeah. So that is first part I like share with all of you about this what we did about the review. Yeah. Next is we're going to the problem is integrate supply chain optimization problem as one example. This is a location production routing problem. We use machine learning assisted to combine with neural network and genetic algorithm to solve this problem. Yeah. This is a joint work with my PhD student, Bahner. Yeah. He just actually had a defense this week. Yeah. And here is about motivation for this project or this problem. First, we look at from the integrated supply chain optimization. When we try to solve some problem concern more aspect in the supply chain different stage, we will increase complexity of the problem we face. So usually we will use integrated supply chain optimization model to formulate the problem. For example, we originally have a inventory problem, and we have a logistical problem separated solving. But right now we combine them together. For example, inventory and loading problem or logistical problem. This is very real situation. For example, Amazon, they have a lot of fulfillment center. Yeah, that's how to decide the inventory and also serve the different area, how to deliver to the customer in the, for example, one-day delivery process. And that is integrated together for the problem. And a lot of this kind of integrate the problem. So here, because we focus on the supply network, we just mentioned here, location routing, production delivery, and location inventory, and also, for example, layout and production planning. Those problems originally are addressed separately, but we right now put them together. So here, one of the problem highly related to all the problem is location, inventory, routing problem. We need to decide the location. For example, can be the manufacturing facility, can be distribution center. And inventory, definitely we need to decide the inventory level to satisfy the serve the area. And the routing problem is usually, to decide which customer will visit in that route, the problem. So they combine those together. So this is one motivation we address this problem. And the second one is about the additive manufacturing or 3D printing technology. This is a technology right now already wide applied for many areas, for the automotive parts, and for the medical implants and the dental some parts for that one, and also for different industrial. Yeah. So I like see, you can see those machine from very simple or 3D printing can be very heavy additive manufacturing equipment. Yeah. So we have a lot of different equipment for 3D printing and additive manufacturing. So with this kind of additive manufacturing, we have a lot of advantage. Yeah. For example, we don't need expensive molds and the tooling for that, and we can save the material, and also the resiliency due to the small supply chains. Yeah. One important aspect for those 3D printing and additive manufacturing is usually easy to move and set up compared with classical manufacturing equipment. So this will increase or enhance the flexibility of the manufacturing network. So with this kind of features, original centralized manufacturing going to the decentralized manufacturing, or sometimes is plentiful, because we have a 3D printing, easy to moving, and can to set up in the different locations. That make us more close to the customer, close to the market. Yeah. So, but with this kind of equipment, we have need to decide every time, every period, what is the production amount for each location. So this will introduce the new feature. This is about the production planning. So the original location inventory loading problem will transfer or change it to the new version of the problem is a location production loading problem. Yeah. So you can see original LIR go to LPR. Yeah. I like to see even our motivation is concerned about the additive manufacturing, but this kind of modeling and also related solution method is not limited to AM based manufacturing situation, because any situation, for example, we have a flexible manufacturing in the different multiple locations, we can use this model. So here for this problem, we concerned facility location, capacity lot sizing, and the loading problem simultaneously. Yeah. So I like to see this kind of this is a variant of a location inventory loading problem. Of course, this problem is similar like LIR. It's harder to solve, and especially for large scale. Yeah. So when we look at the load solution method, we first look at the solution method for the location inventory loading problem, because this is a highly related our problem. So here is a good review about the location inventory loading problem. Of course, we have many different methods. For example, exact based method, hybrid method, meta heuristic, and other heuristic. For this kind of problem, of course, we can use decomposition method for this problem. Yeah, we can see meta heuristic based on this table are widely used for this kind of problem, and especially GA is one of the most side work or method to solve this kind of problem. Yeah. So also, I like to see there are a couple of optimization method linked with machine learning applied for this kind of problem. Later on, we'll mention it. So here we have a motivation is, can we use a machine learning method, combine machine learning with other method, for example, genetic algorithm, to solve this kind of problem, location, production, routing problem. So that is what we think about. So we give a hybrid machine learning based solution method to solve a large scale problem. Use both machine learning and generic algorithm. Yeah. So machine learning method has been used for different supply chain optimization problem. Many those kind of methods like end-to-end modeling and hyper-heuristic and surrogate and reinforce, and also like the learning to optimize those kind of methods. But I like to say most reported machine learning based optimization methods are mainly used to solve individual optimization problem, like the routing problem, like scheduling, like inventory, those kind of problem. Mostly just individual problem. It means not many those methods address integrated optimization problem, but they do have some of those methods linked with our problem. For example, here are the 4 papers we found use machine learning based method to solve integrated supply chain optimization problem. First is the paper by Wu. They used a cluster method to address capacity production distribution problem. This problem also is similar to our problem. They have a capacity production. They all have a distribution, but they don't consider the routing problem on this spec. In the methodology, they use a clustering method combined with a genetic algorithm. Use a clustering to help genetic algorithm, for example, crossing process and other process for that. And the second paper is about the Alice use those constant keyman cluster method to address those hybrid truck Zhang delivery problems, those integrated optimization problem. And most recently, China implemented a surrogate model for capacity location routing problem. So capacity location or routing problem. They mainly use graphical neural network. This method, graphical neural network, are used for many integer optimization problem situation. So here is a review about the supply chain network optimization network. I looked the time. I needed to speed up a little bit. So we can see the research gap. So we see there is a very limit on the use machine learning for integrated optimization, and we have this kind of problem have not been addressed. So we proposed a new problem for this situation, additive manufacturing. We develop machine learning based optimization. Mainly we use two neural network surrogate model for estimating the cost of routing and the capacity lot size and problem. So here is location routing, location production routing problem. We have 3 levels. Level 1 is location allocation, and another level is lot sizing and the routing problem. We formulate this problem that is basically the decision variable is linked with the location, production, capacity production, and the routing problem. We have an objective to minimize the total cost on those aspects, and we have a different aspect, for example, capacity constraint and the vehicle loading problem, the model. The methodology for this problem is we combined machine learning with a genetic algorithm we call the neural genetic algorithm. First two level, we use genetic algorithm to address those decision problem. And the last level, those two problems, we use a neural network, use a surrogate model to estimate the cost. Yeah, we can use this represent the genetic algorithm method to represent the solution. And we use machine learning for those two problems. This is the parameters we have. And here is our training those surrogate model for those two problems, TSP and also for cassette lot size problem. You can see those very close. The arrow is limited, especially for the capacity lot size problem. The good thing is we don't need to get exactly the cost. We just estimate the cost for each console for that. Yeah. So here is our result for the situation. We have like the size 25, the customer, the 5 location, and also 35 to 7. We compare with the simplex with our method. You can see, look at the for the small problem, we have many problems get the optimal solution or method, and for large size a little bit, we can see that after 1 hour simplex cannot get the solution, optimal solution, but they have a feasible, and time is put along. So you can see the time compare for the simplex, for example, for large scale, always 1 hour, of course, but for all is just 35 to 40 seconds, and the gap is 4.1 average, and another 2.1. So I like to say this is pretty good for the large size situation. Yeah, and we have also compared the machine learning with heuristic or solver for comparison. We can see this kind of surrogate model can be increased 2 to 6 times compared with the heuristic, and 50 times compared with the solver. Yeah. So we also tried a mini case and show the result. Then this work already published in the IJPE last year. So if you're interested, you can look at this paper. And then we proposed the improved method, which we call the clustering neural network algorithm. Mainly 2 aspects. One, we introduce a cluster algorithm to improve the location allocation stage, and also limited the search space. We use the K-mean clustering method. Another aspect is we introduced a lower bound analysis, because for large scale problem, simplex cannot provide the good lower bound for us. So we develop a lower bound for the problem. And this is a cluster stage. We have a cluster for the locations and for the customers. And this is the main stage. We have a hyperparameter design for that one. This is about lower bound ideal. So we separate those problem to the 2 sub-problems. One is location allocation with the capacity loss sizing, and another is location allocation with the loading problem. For each of them, we give a lower bound, and then we can find the lower bound among those 2 by maximum 2 of them. But the lower bound for this location allocation loading problem still difficult to solve it. This is because of loading problem. So we introduced logistic-based bundles decomposition for lower bound. then we have a good result for that one. Yeah. So here we have a not only small size problem, we have a large problem for a size from 50 to 100, and the facility also increased to 15 situation. Then we can see the performance. Yeah, performance for the category 1 for small size problem, category 2 middle for large scale problem. For large scale problem, mainly compared with the lower bound we developed. We can see for small size problem, average the performance like the gap. The CPLEX 1.3, we also have a 1.3, but the time is we have a much less time. And for the large scale, we don't have a CPLEX result because size issue. Average the gap is 6.5. We compare with our lower bound. Yeah. We also applied this method to a real case from the paper we published in 2022 about the healthcare situation. We have 78 hospitals there, and also have those information for hospital set VMI location decision. Yeah. So then we have the result for this real case. Real case we can see for the original genetic algorithm, neurogenetic, and next is with clustering method. We can see with clustering mean clustering method, the performance is much improved compared with, for example, gap. For the good situation for the configuration 2, we have a 13.5 gap, but for the improved method, we only have a 3.79. CPLEX got 13.81, but also the time is very fast for this problem. Yeah. So conclusion is we developed for this project developed a location parking routing problem, which is motivated by AM but not limited for situation. We developed the machine learning based method generic algorithm to solve the problem, not only for the random and also for the real case, and the gap is very reasonable, also good. I like see for the situation. Yeah, for that that is what we have. And here is a reference. Yeah. Yeah, and the other case I will not mention. So that is my presentation. Thank all of you.
Thank you very much, Professor Zhang, for such an insightful presentation. Indeed, it generated great ideas, and I was just completely lost in the new trends that are now prevailing in supply chain. So the floor is now open for questions. Please ask questions to Professor Zhang if you have any. Okay, so maybe I will just begin with one to warm up and then the others can follow. So in supply chain, Dr. Zhang, you mentioned about, big data, machine learning, additive manufacturing, and many more things. But we as supply chain researchers, have worked with very less data in the past. So of course, we are anxious to, apply all these new data-oriented techniques and data-oriented methodologies which are coming in the market. So how can we go forward in that, given that, we are not data experts, but we have, we are seeing this new trend and we want to be with the, current trend. So what is your advice on this?
Yeah, thank you for your question. That is a big question, and also is very important. Actually, as we see, we applied a lot of new technology like the IoT. The data going to increase available. I like see because those technology, but as you see, we are not expert in the data analysis, even the collect those data. So this is a challenge, I understand. So what I think is, first is we can start with a limited size problem to look at the available data to try to find the insight. Then go to extend to explore the large range for that problem for that. And the second aspect, I think we probably need help from people work on the data analysis expert on this area to work together to address those problems for that.
Yeah, thank you very much. And second question is, because there are some PhD students in the participant list, you presented very good literature review on the area. So those who are beginning, what is your advice on how to do a good literature review? Because many of them are PhD students and some are even starting. So based on your experience in this area, and you are reviewing so many grants and papers and are serving on the editorial board. So please say a few words on this.
Yeah, thank you. Yes, I like to review is important and also the basis for our research. So if we already choose a topic for our research thesis, then we need to do the literature review to narrow down. So if we do the literature review, I would like to suggest to start look at the topic published in the recent years, especially from those good reputation journal, and with the review already paper published on the topic. I would say that is a good start. Then I would see if we already have a focused topic. Then based on the review paper, we can go further review on that area to get more updated information. Because the review paper for those areas usually is not updated, or because time period the review already have a new work. So we always need to keep open to those new published work. This happened to our group also before. A student already done the work, but they later on realized at the same time, same work published. So we need to pay attention, even we already started work on the project. Yeah, for that.
Okay, thank you very much, Professor Zhang. It was such a nice presentation. Thank you for making yourself available, and we now acknowledge our speakers. Thank you once again, Professor Trepanier and Professor Zhang, for making yourself available. It was great having you with us. We have stored a recording of the presentation, and I will be sharing with you after the presentation is over. If you have any questions or concerns, please let me know. Thank you once again, and have a wonderful time.
Thank you.
You all. Goodbye.
Bye-bye.
Bye-bye.